A sampling distribution is a probability distribution of a given sample statistic. So if I'm looking for the sampling distribution of means, what I'm looking for is taking a population and repeating experiment over and over again, taking lots of different samples from that population, finding the mean value for them, and then what I'll end up with is a whole bunch of mean values, each of a sample. So I'll have this sample statistic of the mean for all of these different samples, and I can make a probability distribution of that. And that is my sample distribution of the mean. Now, that would be if I had one population. Now, I might be interested in comparing two populations. And one way that I could potentially do that would be to take samples, lots of samples from one population and lots of samples from another population, and every time I take a sample from each, I find the difference between the two means. And then I do that again and again, and what I'll end up with then is a collection of differences between two means. And when I do that, then I can actually have a probability distribution of the difference between the two means, which would be a sample distribution of the difference between means. Now, this is a useful tool in comparing two populations to one another. If the means difference is practically zero in all of these samples, then I have two populations that are practically identical. And if the differences are large, then my populations might be very different from one another. Now, you can probably see potential flaws in this, and there definitely are. But as we take more and more samples, the likelihood that those flaws are really entering the picture diminishes. So as we take more and more samples and build up this probability distribution of the mean, we can actually start taking all of these sample means and making some hypotheses about what the population mean is. So let's take a look at the central limit theorem. The central limit theorem tells us that if the mean of a sample, a random sample, of size n is taken from a population with a given mean and finite variance, then we have this limiting form of the distribution. And we have a way of computing z using the mean from the sample and the mean from the population, and the standard deviation from the population, and the square root of n. Now, as n approaches infinity, then what we have here is actually the standard normal distribution. So the underlying thing that's at work here is if we have a large enough sample size, then even if we don't know what this distribution actually looks like, then we can successfully approximate it as normal. So a big question that might be in your mind is, well, what does it mean for the sample size to be large enough? Well, a general rule of thumb is if the sample size is greater than or equal to 30, then we don't actually need to know what the shape of the distribution looks like. We can approximate it as normal. However, if n is less than 30, we need to check about whether or not the distribution is actually normal to be able to use a normal distribution. So this idea of the central limit theorem can also help us come up with some reasonable values that the population mean might actually be. And you need to do a thing called hypothesis testing to do that. Hopefully later in the semester, we will get to talk about that a little bit. But that's one of the consequences of this. But for right now, what we're going to use is this idea that as long as our sample size is greater than or equal to 30, then we can use a normal approximation to talk about the probability of different outcomes. And that if it's less than 30, that we need to check to make sure that it actually has an approximately normal distribution for us to be able to use the normal distribution stuff. So it turns out the central limit theorem can be extended to the case where we're looking at the difference of means. To do this, we're going to need two independent samples of size n1 and n2 drawn at random from two populations. Now, those populations will have means and variances of their own, and then we're going to be taking a look at the sampling distribution of the difference of the means. Well, as long as those n1 and n2 are large enough, and again, 30 is the magic number for each one of those, then we can approximate the mean and the variance of a normal distribution for these. And for the mean, we just take the difference of the two population means. And for the variance, we take the variance divided by the sample size for each population, and then we add them up. So then we can define a random variable z that approximates a standard normal variable for us using these population mean and variance approximations that we found.